Ladies and gentlemen, welcome to our second part of the Structural Geology course, in which we talk about tectonic settings. Here in the chapters 5 to 8, we will, after an introduction, talk about extensional settings, rifts or lacogens and back arcs specifically, and then in a series of case studies, contractional settings in the Andes, Japan, Himalayas and the Alps. Transform settings in the San Andreas Fault and in New Zealand are completing this course, and you can read up about a little bit more background in Van der Ploem and Marschak's textbook in chapter 16 to 19. Here we see an overview map of the important lithospheric plates on Earth, and the boundaries between these plates can be classified in 4 important types. 2 of them are essentially found in the oceanic environment, in oceanic lithosphere, mid-oceanic ridges, where new oceanic lithosphere is created. The mid-oceanic ridges show often offsets along transform faults, and transform faults are most common in the oceanic environment, but we also find sometimes transform faults cross-cutting through continental lithosphere, such as in the San Andreas Fault in California and the Alpine Fault in New Zealand. Subduction settings are found in the intraoceanic environment, where oceanic lithosphere is subducted underneath other oceanic lithosphere. And of course we find the classical Andean type subduction zones, where we have active continental margins under which oceanic lithosphere is subducted. Collisional zones are currently seen essentially between Gondwana-derived small plates, such as India or the Iran plate, which are colliding with the Eurasian plate, and that forms the Himalayan and Alpine orogenic belts. Let's revise briefly the Wilson cycle, starting with a consolidated continent which becomes unstable and forms rifts. We see that in East Africa currently. Such a stage is followed by continental breakup, and we see that, for instance, in the Red Sea stage, but also in the Atlantic stage, where a widening oceanic basin separates initially connected continental lithosphere. And we know that the oceanic lithosphere is not as long-lived as continental lithosphere, and oceanic basins tend to close, and this happens almost always via Andean type continental margins, where we find subduction zones in which oceanic lithosphere is destroyed. Oceanic basins subsequently will close, and continent collision will take place. These new larger continents now get consolidated by erosion, and we form a cratonic environment, a cratonic continental plate. And from there, obviously, the cycle can start again. Here we see an overview of the important contractional tectonic settings, where we find subduction zones underneath continental lithosphere forming accretionary prism and trenches and forearc basins. We find associated with such settings foreland basins and foreland thrust belts, and of course Andean type magmatic arcs. Where continents collide, we get the alpine type continent-continent collisional settings, which of course is a contractional settings. Along continental margins we might find accreted terrains. These are microcontinents which are contributing to continental growth. And we might find forearc basins, accretionary prisms, and also arc magmatism in intraoceanic zones of convergence. The important extensional settings are in some way always related to intracontinental rifts. Consolidated continents are breaking apart, and they form new oceanic basins with mid-oceanic ridges. Associated with that are the formations of passive margins, which do not have ongoing extensional tectonics, but they are a product of such extensional tectonics. And we also find spreading in continental back arc basins, which are very similar to intracontinental rifts, but they are related to nearby subduction zones. And a similar counterpart to this intracontinental back arc spreading we might find back arc spreading in intraoceanic back arc situations. Let's have a look at the forces that are controlling Phanerozoic and also Proterozoic style plate tectonics. Here we see again a sketch from Van der Ploem and Marschak's textbook. This illustrates what kind of drivers and resistance we find in as important players in plate tectonics. Let's have a look here at this basal drag force that we see highlighted here. Basal drag is assumed to be important where we have large-scale astenospheric convection, which would drag and move the overlying lithospheric plate in lateral directions. This assumption is based on tube-shaped convection cells, and modern simulations and observations suggest that these convection cells that have been assumed in the past are actually not that regular and not that simple. We see here an old two-layered convection cell model where we have a deep mantle convection and a shallow astenospheric mantle convection that was seen as a main driver of plate movement. This is probably too simplistic. The real kind of mantle convection cells are much more complex in geometry, with domains that are upward moving and other domains that are moving downwards. You can read up on that in Marschak's first year textbook. So the basal drag force that is highlighted here in this illustration is probably less important than it was thought to be in the past. More important is the ridge push force, which is essentially controlled by the topographic difference between the highly elevated low density lithosphere along the mid-oceanic ridges, which cools down during lateral spreading. Spreading is obviously related to the continuous new creation of lithosphere along the mid-oceanic ridges. So this low density hot material will cool down laterally and then undergo thermal subsidence during cooling. Also the oceanic lithosphere will thicken during cooling, and due to this gravity controlled process we will spread the mid-oceanic ridge and increase the ridge push force. This is one of the main drivers of oceanic spreading and lateral movement of oceanic lithosphere. Then the slab pull force acts in the same direction. We see here the ridge push is spreading laterally and is moving laterally oceanic lithosphere away from the mid-oceanic ridges. The slab density increases downwards and is anyway quite high. We need to understand that the oceanic lithosphere has a higher density than the underlying astenospheric mantle, and if such oceanic lithosphere is brought into an inclined position along active plate boundaries, we will find a density-driven downward pull which is intensified by phase transformations in the deeper part of the oceanic subduction zones, where phase transformations will increase the density even further and convert the oceanic mafic material into eclogite. Resisting forces are, for instance, the friction along transform faults. We know that mid-oceanic ridges are not linear over very long distances. They step sideways, which has something to do with their creation during continental breakup. And these segments are connected by strike-slip faults, by transform faults. Along these transform faults, the friction will counteract spreading. So friction along transform faults is a force that slows down mid-oceanic spreading and the lateral movement of oceanic plates. Another resisting force is the friction along the interface between the upper and the lower plate. The lower plate is always the subducting plate. This force is called the Continental Resistance. This is not necessarily a continental plate. It also could be another oceanic plate that is here more or less coupled with the downgoing plate, and the extent of this coupling will control the magnitude of the resisting force along such an interface. Here the presence of soft or wet sediments in the trench will have a major influence on coupling or decoupling of these two plates, and the easiness how the subducting plate can slip underneath the overriding plate. The subduction rate also plays here an important role, because we know high rates of subduction and fast deformation along such an interface requires higher shear stresses, and therefore resistance might be higher compared to a slow, low strain rate subduction. We see here a topographic feature that can contribute to the extent of the resistance along such interfaces. The coupling of these plates will depend on the topography of the subducting plate. If we have a strongly segmented topography along the upper part of the downgoing slab, we might actually increase the resistance, and we might even produce a process that is called tectonic erosion, which creates a high resistance, a high shear resistance along the interface between overriding and subducting plate. A last resisting force is the friction and the drag along the interface between the subducted lithospheric plate and the overlying astenospheric mantle. We know that here between the subducting plate and the overriding lithospheric plate there would be a astenospheric mantle, and this astenospheric mantle will create a resisting force because it's a viscous material that needs to flow along the interface of the subducting plate. And here the magnitude of resistance is again controlled by the subduction rate and by the mantle viscosity. The mantle viscosity is a parameter that depends essentially on water content, melt content, and temperature. So the hotter the astenospheric mantle in this area is, the less viscous it will be. Magmas generated on top of the subducting plate also can contribute to strain softening, because obviously these melts have very low or no shear resistance. Again, the subduction rate is important, and here we might remember what we have learned in the second year course. We see here that the strain rate is an important factor that controls the shear strength of rocks. So if we have a fast subduction underneath the continental or overriding plate margin, we will be dealing with relatively higher shear strength of the mantle along the interface between subducted and overriding plate. If the subduction rate is low, we will have a low strain rate, and subduction resistance might be smaller. Thank you very much.